Last time on Why This Universe, we dove into arguably the biggest open question in modern physics, the question of how to combine quantum mechanics and general relativity, two incredibly successful and yet incompatible theories, into one more holistic theory of quantum gravity. We explored why this theory of quantum gravity is so sought after and why it's been so difficult to develop. In the search for a theory of quantum gravity, physicists have developed a very notable attempt. You may have heard of this famous attempt before. It's called string theory, and it may be the most promising candidate we have for a theory of quantum gravity. There is so much to say about string theory that this will actually be the first episode of 3 on the topic. So buckle up and let's learn string theory.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and a regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's kind of like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee, and all in the comfort of your own home or daily commute. Recently, I've been listening to a series in Wondrium entitled Understanding Russia, A Cultural History. Over 24 lectures, this course covers everything from Ivan the Terrible and Peter the Great to the role of the Russian Orthodox Church in the Revolution of 1917. It's given me some important background that really helps me understand some of the events that are going on in our world today. So if you want to learn more about Russian culture and history or just about anything else, give Wondrium a try. You can sign up for Wondrium now through our special URL to get a month of unlimited access for free. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper.
String theory is an extremely complicated landscape of ideas, and yet it comes down to one foundational idea that is pretty easy to state. This idea is this: that deep down, the objects we think of as fundamental particles aren't actually point particles at all. Instead, they're strings. Zooming into an electron or a photon, for example, you'll see that at some point, what you thought was a zero-dimensional point is actually a one-dimensional object that we call a string. It sounds quite straightforward, but you might be wondering why this little change would make all the difference. And to understand this, let's go a bit more in depth about why the point-like particles we previously thought of aren't doing the trick.
In ordinary quantum mechanics, or quantum field theory, the fundamental objects that occupy our universe are point-like particles. This means that things like electrons, photons, quarks, and neutrinos are all zero-dimensional objects with no spatial extent. This led to problems when we tried to construct a viable theory of quantum gravity. This problem stems from the fact that in quantum physics, the wavelength of a particle is inversely proportional to its energy. This means that at short distances, you're really talking about high energies. So when you calculate what should happen when two point-like particles get increasingly close to each other, you find that the force of gravity experienced between these particles just gets stronger and stronger without limit, yielding results of blow up to infinity, which of course doesn't make any sense.
In other words, we typically think about the force of gravity as getting stronger the closer you get to the source. But if you had some mass or energy concentrated in a zero-dimensional point, there would be no limit to how close you could get to it. Meaning that at tiny distances around the point, you would experience an increasingly large force of gravity all the way up to infinity. This just doesn't make sense. A single photon or electron shouldn't be able to exert an infinite gravitational force.
The standard mathematical procedure that we use to do these kind of calculations is called renormalization. And while renormalization works just fine for the forces of electromagnetism and the strong and weak nuclear forces, it just doesn't work when we try to do it for gravity. when we talk about this, we say that gravity seems to be a non-renormalizable force, at least if we consider things that are point-like particles.
Here, we're talking about quantum mechanics describing particles as being point-like. That may sound a bit confusing to those of you who know that it also describes particles as being wave-like.
Yeah, so, an electron is a zero-dimensional point, but that point happens to be in a bunch of different places at once. That's the wave-like nature of the electron. But still, if you measure the location of an electron, you find that it's at one place, at least in standard quantum physics, point-like quantum physics. In string theory, the fundamental objects that are found in our universe are not point-like particles. Instead, they're objects with a finite spatial extent. The simplest example of this are one-dimensional strings. A string could be maybe a closed loop or some sort of string that's connected to other objects on either end. And modern string theory also includes more complicated objects like sheets or membranes and other even higher dimensional objects as well.
So string theory solves the issue of nonsensical gravitational force calculations by spreading out any particle's mass and energy over a small region of space. That means that you can no longer get infinitesimally close to the point where the mass is anymore, because the mass is no longer concentrated in one point. Instead, it's spread over some one-dimensional string, or maybe a higher dimensional object like a sheet or a membrane. Changing the foundational idea of the shape of particles ends up fixing this major flaw in our calculations. You could also think about this issue in terms of density. Having any mass or energy concentrated in an infinitesimal point of zero spatial extent means having a point of infinite density. Density is mass divided by volume, and when your volume is zero, you can imagine that division by zero could cause some unhappy issues.
String theory has a long history. It wasn't originally envisioned as a theory of quantum gravity. Instead, it was kind of proposed in the late 1960s as an idea for how we might understand the strong nuclear force. In this context, string theory turned out to not work very well. Instead, the theory known as quantum chromodynamics, or QCD, turned out to be the right theory. QCD describes a strong force in terms of gluons, and it says that things like protons and pions and stuff are made of quarks that interact through this force communicated by gluons. But anyway, QCD quickly became the accepted theory as the data came in and supported it. And string theory was kind of discarded at that time. It was like a thing that was tried that didn't work very well when something else worked a lot better. And it was just kind of put on the ash heap of science history, at least for the time being. So by the mid-1970s, physicists started to notice something else about string theory, though. And in particular, they started to imagine that it might have something to do with the problem of quantum gravity. To understand why they thought that string theory might help us to understand quantum gravity, we have to think back to this problem of renormalization. The problem here was that as you get closer and closer to a particle, the gravity of that particle blows up to infinity. This happens because all of that particle's mass and other energy is located at exactly one point in space. But if you could spread out that energy, like spreading it out along a string, for example, then you could avoid this from happening, and you can get a finite and sensible result for your calculations. So at least in principle, quantum mechanics and general relativity could be compatible with each other if there were no point-like objects in the universe, but instead all the objects were made of objects with finite spatial extent, like strings or other sorts of objects like that. If the known particles, like electrons, photons, or whatever, were actually made up of strings, you might think that we would have noticed this already. After all, we've made a lot of measurements of things like electrons and photons, and none of these experiments seem to indicate these things are stringy. So if we want to explain this, we have to imagine that these strings are actually really, really small. So maybe they're like these closed loops, like I said before, but those closed loops might be something roughly the size of what we call the Planck length, which is about 10 to the minus 35 meters. So 10 to the minus 35 meters is really, really, really small, even by the standards of particle physics. And we just don't have any experiments that could tell the difference between a loop of string that's 10 to the minus 35 meters in size or a point-like particle. They would just look exactly indistinguishable to any experiment we would try to do today. Like if you take the Large Hadron Collider, for example, like you can probe length scales that are like a quadrillion times larger than the Planck length. So even our best, biggest, most powerful particle accelerator can't tell whether electrons are fundamentally point-like or strings. It's kind of like looking at the planet Saturn in the night sky. So if you just look with your naked eye, it looks like a dot, it looks like a point. You get even a kind of rudimentary telescope like the one Galileo built or used, you can see it has rings. So, if you have a sufficiently powerful experiment, you might be able to one day tell that an electron is really a loop of string or something. But with our current tools, we just don't have the ability to figure that out or not.
That also makes string theory effectively untestable with our current technology. To some people, an untestable theory is basically a useless theory. After all, what good is it if you can't test your predictions and determine whether your theory is correct? But to other people, it's worth exploring the possibilities and seeing it through in case anything comes of it.
Okay, so now we're starting to get an idea for why it might be at least possible to build a self-consistent theory of quantum gravity in the context of string theory. Namely, the finite extent of the strings can prevent these calculations from blowing up to infinity as you go to really short distances or really high energies. But it turns out the string theory's potential connection with quantum gravity is compelling for other reasons beyond this as well. To appreciate these reasons, we need to consider the kinds of particles that communicate different forces in nature.
When we say that forces are communicated by particles, what we mean is that quantum mechanics describes these forces as an exchange of a certain kind of particle called a boson between whatever two particles are interacting by a force. That means that there's no action at a distance happening when particles are interacting with each other, even if those particles are separated a bit in space.
The force of electromagnetism, for example, is communicated by particles called photons, the particles that make up light. And since the electromagnetic force can act on particles that are separated across great distances, we know that the photon has to be really, really light, probably exactly massless. The lighter a particle is, the longer the range of its corresponding forces. And if you look at other sorts of force-carrying particles like the gluon, that's also massless. The weak nuclear force, in contrast, is a very short-ranged force, so the W and Z bosons that communicate that force are massive. So we can learn things about the kinds of particles that communicate forces by the characteristics of the force itself. Also, if you consider the fact that the photon interacts with particles according to their electric charge, it turns out that the photon has to be what we call a spin 1 particle. The spin of a particle has to do with how much angular momentum it can carry. Similar logic applies to the gluons that communicate the strong nuclear force and the WZ bosons that communicate the weak nuclear force. So all of these have to be spin 1 particles just by the nature of what they're interacting with, what they're coupling to, as we would call it. But when it comes to the particle that communicates the effects of gravity, what we call the graviton, which is just a purely hypothetical particle, but in a theory of quantum gravity, there should be something like this, something we'd call the graviton. In this case, the picture's somewhat different. Because the gravity is a long-range force, the graviton has to be massless, just like the photon or gluon is. But unlike the other forces in our universe, gravity interacts with things according to their mass and energy. This is really different from the way that photons couple to electric charge or gluons couple to what we call a color charge. It's just a kind of a different sort of object, and it's more complicated.
The other fundamental forces, the electromagnetic force, the strong force, and the weak force, all have strengths determined by some kind of charge. You may be familiar with the electric charge in the case of electromagnetism, and there are similar but different types of charges for the other forces, the strong and the weak force. These charges are very different types of mathematical objects from mass and energy, which determine the strength of a gravitational interaction. What this all means is that while all those other forces are carried by spin 1 particles, the particle that carries the gravitational force needs to be spin 2. It needs to have more intrinsic angular momentum. This is all very technical, but essentially it differentiates what gravity is fundamentally like compared to the other forces in a quantum theory.
Okay, so here's where the story starts to get good. What I've said so far is that the effects of gravity have to be communicated by gravitons that are both massless and are spin 2 particles. Furthermore, it turns out, and this is pretty incredible, that any massless spin 2 particle will communicate a force that's indistinguishable from gravity. So, by definition, any particle that's massless and spin 2 is a graviton. They communicate gravity. It is very different than other forces, like the photon and the gluon are both massless spin 1 particles, and they communicate totally different kinds of forces. The strong force and the electromagnetic force are very different things. But anything that's a massless spin 2 particle, that's a graviton. That thing will communicate the effects of gravity. A minute ago, I said that the story was about to get good. Well, now it's about to get even better, at least for string theory. Around the middle of the 1970s, it was noticed that all known string theories automatically or inevitably included a massless spin 2 boson, their particle. In other words, if you tried to construct a fundamental quantum theory that involves strings, it would automatically include a particle that communicated gravity and automatically include a graviton. From this perspective, it seemed like any string theory would automatically be a theory of quantum gravity. So it was around this time that people like John Schwartz and others started to argue that if we really wanted to understand the quantum nature of gravity, we should abandon all these approaches that failed to involve point particles and instead look to theories that included strings. Personally, I find this argument super compelling. Like, you have this idea that maybe you could solve the renormalizability problem of gravity by having extended objects, and then you notice that, oh, anytime I write down a theory with extended objects, I get a graviton. It's unavoidable. Quantum gravity automatically happens in these theories. It really does look like it just falls into place in a neat package, at least from what we've said so far. So around this time, string theory was starting to look pretty promising as a candidate for the theory of quantum gravity. But in its original form, string theory still had a lot of questions that were unanswered or even problematic. For one thing, at that time, the string theories that were out there only included the particles we called bosons. So bosons are things like photons, gluons, and gravitons. But it didn't include anything like an electron or quarks, okay? These things just weren't there in string theory yet. Bosonic string theory, thus, obviously wasn't the whole story. There had to be more to it than that. Another big problem, or at least a potentially big problem with string theory, had to do with the masses of the strings in the theory. Now, the mass, charge, and the other properties of a given string have to do with how it vibrates. For an example, an electron and a quark might deep down be the same string, just vibrating in different ways, kind of like a guitar string might vibrate in different ways to generate different notes. So, if you knew exactly how a given string was vibrating, you could, in principle, work out how heavy that thing would be, how much mass it would have, what kind of charges it would carry, all that sort of stuff. All right, so let me kind of describe, at least in broad terms, what you might do to try to calculate what the mass of a particular vibrating string would be. So to do this, like, picture a string that's maybe stretched across through space and is attached to two different things on either side. The square of the mass of this string gets contributions from three different factors, okay?
So if this was an equation, it would be something like mass squared equals A plus B plus C. A, B, and C are the three different contributions to this mass. In other words, they're factors that determine how massive a given string will be. Yes, we're doing math in a podcast today.
First, there's the rest mass of the string, which has to do with how it's stretched between its endpoints. Okay, so you can calculate that. Second, there's the vibrational energy of the string, which is related to its mass through Einstein's equation equals mc squared. And third, there's the minimum amount of vibration that's allowed by the rules of quantum mechanics. So in quantum physics, particles and strings are usually not allowed to be completely at rest. The energy associated with this minimum amount of quantum activity is what we call the 0-point energy. Okay, so we have these three different contributions, and now we're going to add them together. And when we add them together, we get the total square of the mass of the string. The contributions that come from the rest mass and from the vibrational energy of the string are both positive. Okay, so the first two terms are automatically positive. But it turns out that the 0 point energy, that third term, is always going to be negative.
That means our equation is actually more like mass squared equals A plus B minus C. Why is this 0 point energy negative? Dan and I can't really tell you.
I don't have any clue. This is something I've read in books and on web pages. I don't understand why would the 0 point energy be negative? I don't know. Yeah, it doesn't make any sense to me either.
When you're working with a theory as mathematical and abstract as string theory is, sometimes you're just left wondering what all this math is really trying to tell you. But moving on, that minus C in our equation ends up having some weird side effects. If this negative contribution is greater than A plus B, then the total mass squared will be negative. Taking the square root of a negative number leaves you with an imaginary answer. That's actually a technical term. We call the square root of -1 I, and it's the imaginary unit. All this means that the mass of the string would be an imaginary number.
This is a big problem. Particles with or objects with a imaginary mass are what we call tachyons, and they always travel faster than the speed of light. And they kind of ruin your theory. They make things like logical, coherent structure of causality and all that stuff impossible to maintain. You end up having paradoxes, and basically your theory breaks. So any theory that has tachyons in it is a sick theory, a broken theory, and you have to throw it out. So we have to be sure that our string theory doesn't allow any of these strings to have a negative value for the square of its mass. In order for a theory involving strings to not contain any tachyons, the combined size of these first two terms has to be larger than the negative contribution from the 0 point energy. If this is the case, then our theory will be tachyon-free and we'll be in business. We can actually be more specific here by noticing that in our universe, there are some particles, like the photon and gluon, that have exactly no mass. So there have to be at least some of these strings where those first two terms, which are positive, exactly cancel with that third term that's negative, giving us exactly 0 for the mass squared, and therefore 0 for the total mass of the string, at least in some cases. And, you can do this calculation, and it turns out that if we want to both avoid tachyons all the time and allow for massless strings, you have to live in 26 dimensions of space and time. Any more or any less than 26, and you either have no massless particles or you have tachyons. You just don't live in a universe like ours. To understand why the number of dimensions comes into play, it really has to do with the 0 point energy. If you have more dimensions that you can vibrate in, quantum mechanics says you're going to vibrate in all of them, making the size of that third term different. And it turns out that if you pick 26, then you can get massless particles like photons and gluons and no tachyons. Any other number, and it just doesn't work.
This is the point where if you've been following along until now and you're like, oh yeah, like this sounds great, this is great. This is the point where you're like, wait a second.
Yeah, like, okay, string theory seems to solve the renormalizability gravity. Great. Oh, string theory predicts gravitons automatically, so it's automatically a theory of quantum gravity. Great. Everything seems to work. Awesome. Oh, but you have to do it in 26 dimensions of space and time. That's not reassuring. So next time on Why This Universe, we're going to pick up where we left off here today and talk more about string theory. We'll describe some of the different kinds of string theory that have been explored over the years and talk about how they're related to each other through what we call duality. And we'll talk more about those 26 dimensions of space and time, how they might be hiding from us, and how we might be able to find them one day in an experiment.
Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.